G'day everyone. It's my absolute pleasure to welcome Jackson as our very first kind of open science meeting speaker. Congratulations, Jackson. You were the top of our list. Jackson's a member of the Green Group at MIT, one of the core developers of Chemprop, a prolific open source contributor, and also participant in our various challenges. Um, and we've been using a lot of his work internally at OpenADMET with some pretty good results. So it's my pleasure to welcome Jackson today.
Thank you very much, Hugo. I'm flattered. Let me get the screen share going up here. All right. So we tested before, so theoretically it's working again. But um, yeah, I appreciate everybody being here today. Um, it's really an honor to be the inaugural member of this series, so I hope to make it worthwhile. Um, Today, I'm going to talk through the model that I think most of you have probably heard of. It's been all over the leaderboard on the latest challenge, which makes us really happy to see. That model is Chameleon, which this title has been fluctuating because we're trying to get a paper actually out about it out of preprint, but we're calling it the descriptor-based foundation model for molecular property prediction. So, with that said, I guess I can't have this thing on because then I can't advance the slides. Good to know. All right, just a quick agenda. We're going to go about, I think we said 30 to 40 minutes. I'll start, I'm going to do slightly reverse order. I'm going to do some acknowledgments first because I feel like a PI here. I'm presenting some work that other people have done, so I want to make sure that they get their flowers before I talk too long and go over and skip it. Talk a little bit about myself, then Chameleon, some of the history of the model, maybe the most important question, does it work? And we'll try to introduce as much nuance into that question as possible. More exciting, perhaps, is where to next. So we have lots of open ideas. I know internally here at OpenADMET, you guys have had some ideas as well about, what do we do next with this idea? And I'll leave that for then. Then right at the end, I have just a brief tangent about Chemprop V2. As Hugo mentioned, I'm one of the core developers over there. We just had a ground up rewrite and we released a paper about it, but I realized we never actually explained why we did it. So we'll talk about that right at the end, just for a couple minutes. And I have this in a big pop-up here. Please interrupt me. At MIT is sort of unique in that there's an expectation that as you're giving a talk, if someone's confused, they'll interrupt right there. So it makes thesis defenses really fun too, but throws people off their game. But yeah, please interrupt if you have any questions as we go.
Can I kick that off with an interruption?
Yeah, please do.
Uh, why is the M capitalized in chameleon?
I like that question. So, chameleon is derived from two things, from chemprop, obviously, and then from the Mordred set of descriptors. So Mordred is the Arthurian legends character. He was like an evil wizard kind of guy, and the son of him in the stories is named Melion or Melion. So this is just a concatenation of those two that keeps the word chem in it by coincidence. But thank you, excellent question. That we actually worked harder on the name than we did on anything else. So anyway, yeah. So speaking of the team, then. First and foremost, my first co-author, Akshat. Also want to thank Charles, also at MIT, and our collective PI, Bill, and then our collaborators from BASF who joined in this project, Jochen, Christian, and Miriam. And then work individually is funded by the Department of Energy through the Computational Science Graduate Fellowship. So much appreciation to them there, giving me the flexibility to go out and explore fun projects like this. Um, so yeah, there's my acknowledgments. A little bit about me in particular. I was born in the late 1900s, and I spent the beginning period of my life in Edgewood, Kentucky, just a little bit south of Cincinnati. I mention that not because it's scientific, but because I never meet anyone else from Kentucky. So on the off chance that anyone here is, please connect with me. Back in 2018, I did my undergrad in chemical engineering at the University of Delaware. You can go read my really not great thesis, but it was my first step into data science. And in that case, specifically for transition metal catalyzed cross-coupling reactions. So it was all like Aza-Heck chemistry, a lot of those really complicated sort of uh, transition state calculations, things like that, and a lot more experimental work. So then in 2022, when I switched into MIT to get my PhD this go around, I decided to stay away from experiments because I was really bad at them. My thesis these days is exclusively really in machine learning for property prediction. There's a sub part of it that's focused on facilitating kinetics simulations, but today what I'm going to focus on, and what's taking up more and more of my time, for good reason because it's been, successful and we're happy about the adoption, has been focusing more on property prediction for the pharmaceutical space, drug discovery, things like that. And then I will mention too that sometime starting this year in 2026, I will be taking a job at some company in the greater Boston area. I'll be graduating. So if you like what you see today, please reach out. I am more than happy to interview, send some resumes along, all that kind of good stuff. So anyway, back to the topic at hand, Chameleon. If I had to say in one line to most people what Chameleon really represents, it's just this single line as part of their Chemprop training script from Foundation Chameleon. This, to most people, is the extent to which they interact with it. And there doesn't need to be a lot more thought behind it than that, which we're very happy about. Obviously, that was our intention, was to try to make it really user-friendly and accessible. Behind the scenes, what's actually happening when someone does that is they've got some small data set with some, expensive to calculate or measure property that they need to try to model, whether that's for screening or for their own independent discovery pipelines. All that Chameleon does is provide an initialization to the message passing half of their machine learning model. So for Chemprop specifically, we tend to segment it into two pieces: the representation learning directed message passing network, and then the actual mapping of the representation into the property that you care about through the FNN. So at the end of the day, Chameleon is literally just a set of about 8 million numbers. And when you fire up Chemprop with that flag in there, we set your message passing neural network to start from those 8 million numbers and then go through the same exact process as before. So to us, at least, the interesting part of Chameleon, it's nice to have all the good performance, but the maybe academically interesting part is the approach to pre-training. And I think this is what's hinting at interesting future directions. So that gets towards that question of how did we actually build it. So the pre-training scheme is shown on the left there. But again, to keep it really brief, Chameleon is just a Chemprop model that has been pre-trained to predict Mordred descriptors. So the question that we had all the way back at the top of the hour was the name. Chameleon is derived from the combination of Chemprop and then Mordred, which, if any of you haven't heard of them, just a giant vector of 1,600 molecular descriptors, every conceivable thing you could reasonably think of, from, counts of common functional groups up to more complicated things like autocorrelation indices, basically lots of different fun graph navigation problems that chemists in the past have figured out are related to properties that we care about in applications. Just some technical notes that I think might be interesting to this crowd. When we actually do the fitting process, we don't directly predict the numbers and then penalize on every single one at the same time. We're pre-training on over 1 million molecules, but because we have 1,600 targets, every batch actually has quite a lot of signal to it. So to prevent overfitting, in early epochs, we actually use masked mean squared error rather than just regular mean squared error. Essentially, we only penalize on 15% of the predicted descriptors, and that's selected randomly at every iteration. So fundamentally, it's similar to what Chemberta does, for example, with like masked language modeling. They cover up some of the tokens and they predict them and just penalize on those. We only penalize on a subset of the descriptors. So really, this is just dropout. And I think maybe one of the other advantages here was the use of Windsorization. So the original descriptors, as calculated, often have some pretty wild outliers, as I'm sure a lot of you are familiar with when getting, nans in your descriptors. Oh, sorry, I see a hand. Yeah, go ahead, Pat.
Yeah, no, I just wanted to ask why Mordred descriptors and does it make a difference? So if you would have pre-trained on the RDKit descriptors, would it have made a difference?
Yeah, we have spent many hours sleeplessly at night wondering that exact same question. So I think I to be completely honest, the knee-jerk reaction was to go to the Mordred descriptors for the intercompatibility with Python. So being able to call them from a Python API and then being able to write them into, very compressed data formats, just made it really easy to interoperate. Um, we thought for sure that in the initial paper we would need to go back and revisit our choice of Mordred descriptors because we thought the exact same thing. We said, there's 1600 here. We're having to do this masking to prevent overfitting anyway. Surely there's some smaller subset of this that is actually doing most of the heavy lifting in terms of making this model really good. Um, but I think more for practical reasons that, the model turned out to be pretty good anyway. We have not gone back to answer that yet. But in the future directions one, we'll bring this up again because yeah, we are looking at other subsets.
Yeah, just I asked because I've done quite a few comparisons of the Mordred descriptors with the RDKit descriptors, and I find that for the most part, it doesn't seem to make much of a difference. And the RDKit descriptors are way faster to calculate.
Yeah. Yeah, and I'm excited too. I think RDKit will be releasing it's a superset of the Mordred descriptors soon as well, so they should have an even larger set. So maybe we can answer this question by doing the nice small like 212 or whatever it is from RDKit up to the now I think they're going to have like 4,000. So, but yeah, yeah, open question for sure. Um,
Cool, thanks.
yeah. Where was? Oh yeah, Windsorization. Yeah, so clipping basically. Yeah, as I'm sure many of you are aware, when you try to train continuous models on molecular descriptors, especially when you go out of the way to like rescale them, you can get some pretty crazy outliers. So just another fun little technical note. We applied Windsorization based on standard deviations rather than quantiles to the input descriptors, again, just to try to control the fitting behavior, really. And then this is actually getting a little bit into maybe which descriptor set is the best, but right now we have two theories that we're building, and they're opposites, but theories about why Chameleon has been successful. Why does it give you good results? The devil on your shoulder says the descriptors really at the end of the day are not very special. They just are conveniently, something that you can calculate. You know that they're informative purely for the fact that chemists have figured out that they correlate well with other properties. And really, all of the gain that you're getting is not from any fundamental scientific improvement beyond just a regular Chemprop model is going to be initialized randomly. Any deep learning model is going to be initialized randomly. So there's going to be some amount of time that you spend, wandering around a plateau of just uselessness in the actual representation stage. So, maybe this isn't the best way to do it, but just the fact that we've done something interesting, so the model has at least learned a representation, that's better than nothing. Versus, the angel on your shoulder saying, yes, you've hit something really good here. The descriptors do something truly interesting. So in the Mordred set, for example, there's count descriptors for common functional groups like oxygens. If the model is able to, first and foremost, just be able to predict those, that means that it's learned some level of, how to map the graph representation into that. So it's learned that sort of navigation procedure. But that could also be leading it to learn substructures. I think when we think of like Morgan fingerprints, for example, they're generally very powerful baselines for a lot of these tasks. They work exclusively on substructures. So could it be that by pre-training this with these molecular descriptors, the model is somehow learning to achieve a level of locality that is still not global, but is able to localize within these like few atom neighborhoods? It's again a theory. We're looking for first and foremost ways to test that theory, but also other theories. So that could be a good topic of conversation. But I will keep moving here. As a point of comparison, before we go into the, does Chameleon really work? I want to talk about the other models that we included and just give you a little bit of a brief literature review. This is the combined overall training graphic for how Chameleon works. So you see the pre-training on the top and then the fine-tuning on the bottom. There's a collection of models, both closed and open, that do basically the same thing, but rather than calculating and then predicting descriptors, they use just something else. Oftentimes that's, they'll run quantum mechanics simulations and then predict all of the miscellaneous things you can drag out of that, just derived from the electron density. Another popular method, that's what Minimol does, is to predict on experimental data. So just like aggregate tons and tons of pre-measured experiments and then predict those during pre-training. And again, giving the same idea of let's arrive at a pretty good representation and then go from there during the fine-tuning stage. But there's also a sub-collection of models, and there's no graphic for this because they're all very different in how they work, but they train without supervision entirely. So MolCLR was maybe the first one in this space. CLR is contrastive learning of representations. I can't remember the exact way that they cobbled together the acronym, but basically they give it two molecules at the same time, and if the molecules should be close to each other in the original space, the model's learned space will also put them close to each other and vice versa. So it was taken from deep learning for images. I have some evidence that it didn't really work, but we'll get there when we get there. The other common one, and I talked about this with Chemberta, is string-based. So we've included MolFormer as the reference here. It's basically a better version of Chemberta, depending on who you ask. And then I'd be remiss if I did not mention that training without supervision currently is not really possible with DMPNNs, sort of. There are people working very hard to make it practical and really like as easy as this sort of supervised pre-training that we've done. But I won't get into that today, but some of my collaborators are doing that, so they'd be mad at me if they found out I didn't mention it. Great, so the interesting slide then, does it really work? My answer would be yes, usually. So on the left there, we've got the very classic Tukey honestly significant difference test plots on a few different benchmarks from both Polaris and, you'll have to forgive me, the Therapeutic Data Commons. Only kidding, of course. And what we see is that Chameleon, first and foremost, consistently improves over the baseline Chemprop model. So if you look at all of these different benchmarks, so this is LD50, we have solubility, so on and so forth. Chameleon, all the way on the bottom, is almost always moving the performance to the right from a randomly initialized Chemprop model. In some cases, like on hERG inhibition here, Chemprop is almost the worst model, only narrowly maybe beating out MolCLR, which you'll often see very close to the bottom. And Chameleon is able to take Chemprop all the way from nearly the worst up to statistically the best, tied humorously with Random Forest. And again, that trend holds throughout a lot of these tests. The one exception we found so far was with this permeability with Keiko2, again from the TD Commons, where Chameleon, this difference I would speculate is probably not statistically different, but we didn't improve it there, but generally it does seem to improve it. And then when you aggregate this across the many different benchmarks that we ran, so we took out 28 different just ADME benchmarks from the Polaris platform. we did see a nice statistical improvement from Chemprop to Chameleon, taking a win rate from 32 to 75. Really, so we narrowly edged out the minimal and random forest using Morgan count fingerprints with RDKit descriptors. So a nice improvement to Chemprop, but also a little tiny maybe edge out over some of these best models. But really, our impression at least is you can sort of draw a line between Moleformer and random forest. Things above that line are going to always be trading places on some of these really competitive benchmarks, and things below that line, not so much. At least on the data set sizes that we focused on here, which that's a whole separate can of worms. And then the other set of benchmarks that we ran showed maybe even more promising results. So these were about activity cliffs. So this is from the paper where they introduced the molecule ACE, which is molecular activity cliff estimation benchmark. We sort of split this into two halves. So on the left here, and I'll try to explain this plot. The vertical axis is all of the different assays that they introduced in that original paper. And then the horizontal axis is the difference in root mean squared error between the compounds that were in the cliff subset and the non-cliff subset. Cliff meaning it fell off an activity cliff, and despite the changes in those given structures being relatively small, the activity was very different. So we think of this as almost like a consistency plot. So any blue marker indicates that the model had statistically identical performance between the cliff and non-cliff molecules. And then if that dot is filled, that means that it was also the best performer in terms of root mean squared error in an absolute sense. So it definitely, oh yeah, let me pause there. Pat, another question.
Yeah, this is cool. I just don't understand why. I don't understand why pre-training gives you a better performance on activity cliffs. Because ultimately, with an activity cliff, you're saying, I've got two compounds that are very chemically similar that have different activities. So what is the Chameleon pre-trained model picking up on that the others aren't?
Yeah, yeah. So actually, you've hit on something there because if we look at the actual results, Chameleon is statistically consistent between cliff and non-cliff molecules on only four of the assays. So looking at, the alternative, random forest was consistent on only two, but neither of those it performed better than Chameleon in terms of the actual RMSE. Minimal, again, similar story. It was consistent on, let's see, that's six, but only two of them. It was statistically the best performer. So Chameleon, the pre-training is still not able to really, like push apart in representation space activity cliff compounds. The reason that we're still, I mean, one thing, we're showing this result just to demonstrate to people that, this is not, the miracle machine. This is absolutely still, it has its own limits, but um, the absolute performance, if we refocus and instead we say, let's forget about the relative difference, or excuse me, the relative performance between the cliff and non-cliff compounds. If we look, across the entire test set in this case, or if we look just at the cliff compounds, and then we do that same comparison we had on the previous slide, how performant is Chameleon? I mean, in this case, we see a much more dramatic improvement over the next best alternative. So Chameleon, when looking across again the entire test set, almost perfectly getting the lowest possible RMSE on all the different benchmarks. If you narrow down to just the cliff molecules, so if your argument is, well, we really just want to be able to as accurately as possible predict the activity for cliff molecules. This is again going to be your best bet. All the models tend to surprisingly do a little bit better there, but Chameleon again with a big advantage. So not a perfect story at all. We've improved the absolute performance, but not been able to exactly tease out those differences, which we think of with this Wario meme. We've won, but at what cost? It's we're sort of fighting against the nature of the beast here, where the purpose of these models is to embed into a similar chemical space, or excuse me, into a similar representation space, molecules that look similar. So when you run into activity cliffs like this, this sort of suggests to us that Chameleon is not the way to go and identify activity cliffs, but it is the way to just get the best possible performance on the actual prediction of the, response in the assay. Um, Now, with that said, this slide's a little bit more pie in the sky in terms of where to next. We do have one concrete goal, peer review. We submitted this last year and it got desk rejected. So there you go. I feel like Harry Potter, where it got rejected and then hopefully goes on to be a huge success, but we'll see. We've already gained some empirical evidence that Chameleon can be worse than Chemprop on data sets using containing radicals or charges. So I know radical is probably not as interesting here, but again, from a kinetics background, we have to do at least a little bit of that for my PhD part. But charges, there's some interesting questions about, if you want to try to predict, distribution of microstates or pKa given the distribution of microstates, should you be representing the molecules using the charge? It's just one example off the top of my head. And one thing that's come up from our funders. That taken as well with the activity cliff sort of shortcomings there in terms of the relative detection. We have a couple, immediate steps. Like these are the things that are going on today. We're just trying to quantify, the failure modes of Chameleon. We've got some successes and one good failure well represented in the story in the paper. So, we need a little bit more so that we can move on to the next big thing. And then, as I mentioned, there's open questions about, if your model is bad with charged molecules, can you learn on just the neutral parents structure representation? Just a question right now that we'll try as we're going on, but maybe really interesting to this group because I know we're going to have a meeting soon about what new ways we could go. We have sort of two different directions that we're considering for what are we going to do with Chameleon. The obvious one maybe is what Camberta and what ChatGPT does. Just release Chameleon version 2. Where we tune the hyperparameters, we change the number of parameters, and then I'll circle back to those last two in a second here. And we just try to come up with a model that is a little bit better on everything. We do think there's some performance left on the table. The aggregation function that we used, for example, we used mean, maybe norm would have been better. There's lots of knobs to turn there, so we'd like to go back and take a look at that. But there's many questions. We talked about this a little bit earlier. Maybe we need to use fewer or better descriptors that are, more relevant to the tasks that we're trying to fine tune on. Or maybe it's the opposite direction. A lot of these deep learning models have, if we look to like ChatGPT, for example, they tend to improve by just slamming more and more and more data into it. GraphCore, they did a little bit of scaling analysis when they published some of their foundation models. So there's a little bit of an edge that we can use to sort of jump into that direction. But big open questions about both the set of descriptors, the number of molecules, as well as the types of molecules. Being a group of broad interest, we also started from PubChem. So we did only the most minimal amount of processing to remove like particularly giant or like invalid molecules, but really nothing more than that. With our hope being, getting a lot of breadth would help us more so than a lot of very specific like structure filters right at the beginning. So again, that's one possible direction that we're thinking. The other one, and I think personally I'm more inclined to this one, but I also want to say that they're not necessarily completely opposed, is going more in the direction of some sort of a prefix where we say this is charge chameleon, this is radical chameleon. It's basically, and this is an oxymoron, a more specific foundation model. So rather than going for scale and trying to make it generally better, we're going to say, maybe if we are trying to perform really well on ADME, you should only be pre-training on the molecular descriptors for molecules that you reasonably expect to find in those assays. So should we have gone back and filtered out, toxic substructures that aren't stable in the human body, or molecules that are way bigger, or things that are outside of Lipinski's rule of five. There's questions about, should we narrow it down? And similarly about the descriptor sets and how those relate there. But yeah, I see another question from Pat. Yeah.
Yeah, I'm just curious, Jackson, when you're talking about charged, because a lot of the molecules that we're dealing with in drug discovery, we've got basic amines and we've got carboxylic acids and things like that. Is that the sort of thing you're talking about? Or are you talking about more exotic things that you're dealing with in materials or?
No, no. So nothing exotic there. I am talking quite literally about, like, if you put this structure into Chemaxon and ask for the distribution of microspecies, you'll get back, maybe the amine will be protonated at bodily pH. I think so. To clarify, what we did for training is we neutralized everything and tried to get back to the parent species. So almost treat it like a QM simulation and say, just give us the most basic graph, not basic in the chemical sense, but basic in the sense of, like, if you gave this formula to a freshman in a chemistry class, how would they draw it? We just try to go all the way back to that and sort of avoid the question of, if we're making a drug that we know is going to be ingested by a human, so we know that it's going to be at bodily pH, should we represent it with protonated or deprotonated sites as appropriate? So right now, the model doesn't work well if the SMILE strings have protonated or deprotonated centers. So that's the charge that we're referring to. Um, the open question that we had earlier was, can we work around that by, again, operating on this, like, neutral parent graph of the protonated or deprotonated structure? Um, that's something that we're trying to inject more data into. And I think, my impression at least is there's no, concrete field-wide consensus on, if you know that something is occurring at bodily pH, should you protonate the SMILE structure for your molecules? We do know that it will change the predictions, but at least we found a failure mode here, so we're gonna peel on that as much as we can. Um,
I mean, it
and
seems like
then,
it'd be
yeah,
relatively straightforward to just do a side-by-side comparison where you're going with neutralized structures versus things that are at a more physiologically relevant representation. I just
hmm
wonder if it's going to make a difference. I mean, to me, it seems like it's often more important to be consistent than it is to be correct.
yeah, 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 yeah. We've wondered that ourselves, and wondered too the pre-training target, being molecular descriptors. Those generally are designed for the neutral sort of parent graph. So would the descriptor set really even reflect the changes that we're making in the representation? So would the pre-training change at all? Is a good question. So yeah, we've achieved consistency. So now we get to do the fun, digging in a little bit more. Um,
Are you doing multitask pre-training? So are you multitasking against all the descriptors when you train?
That's right. Yeah, all
Okay.
1600 descriptors are predicted simultaneously, and we only penalize the model for every training batch on a randomly selected 15% of the predictions. That's just to prevent overfitting.
Okay.
Yeah, yeah. So yeah, multitask was pivotal here. Yeah. Um, and then I think I sort of mumbled it to myself, but I will emphasize too that, sort of like when you're taking a Scantron test, option C here is actually both A and B. We have it in our head right now that, the two ways to go are, you either try to make a generally better foundation model, or you try to make one that's better at narrower sets of chemistry. Um, in this wonderfully gray world that we have, there's no black and white between those two. We think there's probably a lot of room for, a generally better model that also improves on these sort of specific categories just by the nature of being a generally better model. But it might take some lessons from, the types of molecules, or the types of descriptors. Um, So with that said, I will take a few minutes here to just talk about Chemprop V2. And its relationship to Chameleon and to the broader community. Right before this call, we just released Chemprop 2.2.2, so we're nearing the this not just stable but reduced bug version of Chemprop. Fingers crossed, famous last words. Um, but yeah, what we think of internally is that Chemprop version 1, which maybe fewer of you are familiar with, but if you had the opportunity, you maybe knew it too as a really well-loved research code. So it was quirky at the best of times, and it was a little bit broken at the worst of times. Um, it got what it needed to get done, and it led us into what we have today, which is Chemprop version 2. We think of as a much more well-designed production level type of code. So the code base itself is much smaller, much more streamlined. Everything's faster, sort of as a consequence of that, but we also were able to update all of our dependencies, so everything runs a lot faster. Um, I think what's most exciting to us is the fact that Chemprop has a Python API now. So if you used Chemprop V1 at all and you wanted to try to call a model fitting from within Python code, you had to do something hilarious, like call out to an external shell to use the Chemprop CLI, or you had to like mock the Chemprop CLI internally and then pass it back. So anyway, a mess, not really scalable, not a recipe for success. So Chemprop V2 solves that. Um, as you can see in our nice little table of contents graphic from the paper down there, it's very possible and very straightforward now to use Chemprop in code, just like any other like PyTorch geometric or DeepChem used to be able to do, anything like that. And that has enabled us already to make some pretty significant strides in the group. Chameleon is, of course, one example of that. As I mentioned way back at the start, the Chameleon model is just a message passing set of weights. It's just 8 million numbers that initialize one half of a Chemprop model. Being able to partially load a model in just a couple of lines of code is fantastic to us. That was not possible in V1 really. And then the masking that has came up. So when we were doing this multitask learning and we needed to only penalize on some of the descriptors, that was implemented via a custom loss function. Again, that would have been really annoying to do in V2, or excuse me, in V1. And then, for those of you looking to extend Chemprop as well, not only is it first compatible on all platforms now, but the code base as a whole is a lot easier to integrate with other tools. So we released the Chemprop model context protocol. So this allows you to train Chemprop models using large language models. And the real lift for that in terms of software engineering was just getting it installed alongside the I'm not kidding, like 400 Python packages that need to be installed in order to run LLMs, which is again, we're happy to have that done now, not really possible beforehand. And then I finished these slides last week, so this is a little bit out of date now, but I think that maybe the story is even better. But your own competition that you're hosting right now, back when I wrote this, the top three publicly disclosed models that had enough detail to tell what they were doing in terms of actual architectures. All three of them were using Chemprop in some form, hopefully some of them using Chemprop V2. And I think at least two of them were using Chameleon specifically. So very excited about that. So we're hoping that, we had our own internal frustrations with extending and integrating Chemprop V1. So we're hopeful that with V2, especially as you build up the OpenADMET, excuse me, I'm going to get the name wrong. It was either Forge or Foundry, where you have these models. It's easier to extend, and all of your other packages in the world are ready to integrate this as well. So this is a big add. Go ahead and switch to Chemprop V2. It's much nicer. So with that said, I will say thank you again. Thank you for taking your holiday or for joining at some strange time of day to be thinking about chemistry. You can find a link to the preprint there. It's a little bit old at this point, we have a new title, which is the title of this talk, and hopefully we will be posting the updated version soon. Um, Archive was down for the last couple of weeks, which we used as an excuse to not post it, but now we actually have to finish it. So we're gonna we're gonna get that done. We're gonna have a preprint ready, which will describe everything that I had in the talk today. You can go on the GitHub right now and you can see all of the same results. Um, I'll say connect with me on LinkedIn as well. As I mentioned earlier, I actually am really looking for a job in 2026. So if you like what you saw, please reach out. I also post lots of fun stuff on LinkedIn about these models, and I'll announce the paper and things like that. And with that said, I am more than happy to answer any further questions. And again, thank you so much for your attention.
Thank you, Jackson. I'm going to open the floor to questions. So raise your hand and I'll call out your name, or I'll try. Sean.
Hey Jackson, thanks so much for the talk. I was curious, totally fine if you haven't really pulled this thread at all, but we've been doing a bit of work with uncertainty estimations, and I noticed Chemprop, I'm not sure if it came online with V2 or when, but you have some functionality to do like the negative log likelihood, mean variance estimation, stuff like that. Have you worked with that stuff with the foundation side of things ever?
No, so the foundation model right now is just doing absolute predictions. We did, so during initial stages, we thought about, you know, I think under typical circumstances, when you don't have a ton of samples, it can be hard to bite it can be hard to swallow the argument that the individual measurements you're looking at come from a distribution. But for us, when we were pre-training on this, again, this is a million pre-training molecules, it made a lot of sense to predict a distribution, penalize it as a distribution. Again, so getting into the idea of the uncertainty quantification. Um, it's not included here, and at least partly because for a lot of the descriptors, and this is actually a feature that we like about these descriptors, there is no uncertainty in the way that they're calculated. So, today and Tuesday and in a lab halfway across the world, the number of oxygens in a molecule is exactly the same. And the autocorrelation indices are exactly the same. So even though, the uncertainty, we think it could offer some advantages, given the fact that the targets are certain, we started without it. But yeah, thank you for bringing up that it's in Chemprop V2, because yes, if anyone's listening, and wants to do uncertainty quantification, all of that is implemented in Chemprop V2, very readily accessible via the command line, which I like because all of the uncertainty quantification methods are they're not super mathematically complicated, but they give you a lot of little moving pieces to keep track of. So V2 will take care of that for you. But yeah, thank you for the question.
I'm going to go with Pat.
Yeah, I was curious about what else you guys are working on for Chemprop. One of the things actually that Hugo's been looking at recently is how do we deal with censored or truncated values, where you've got things like greater than 30. And I know that Chemprop has a bounded loss now, which seems to be, I haven't seen a whole lot of examples of people using that. And I wondered if that was the sort of thing that the Chemprop team was looking at. To me, it seems like something that has been unexplored to date and is really important.
Yeah, yeah. So um, I'll get back to the censored one because we have some experience with that as well. And I'll say maybe one interesting future direction for Chemprop. So, in addition to continuing to explore foundation models, whether that's Chameleon or through a self-supervised scheme or something like that, I think Chemprop V2 has a lot of easy sort of modularity benefits to it. So implementing like new featureizers, for example, the Chemprop feature set that we use to describe atoms and bonds has been basically unchanged since the first paper, partly because it was quite complicated to implement new sets. So we're looking at alternative featurization schemes. So rigor from our group. So that was the resonance invariant graph representation. That was our first big step in that direction. And that was just, again, born out of our kinetics background, saying that, there are multiple valid resonance structure representations for a given molecule. Can we have a atomic and bond featurization scheme that does not change if you change the resonance structure that you pass in? So yeah, a lot of it has to do now with a lot of our future directions have to do with, how can we take advantage of this shiny new code base and solve some of those outstanding problems like that. Um, and then yeah, in terms of sensor data, so you're right, we have bounded mean squared error as a loss function. Um, that was the extent to which our funding agencies were willing to pay, so it stopped there. But our experience with it so far has been occasionally when you train censored data using actual censored loss functions, you actually get worse performance than if you just ignored the fact that the data was censored in the first place. And we don't have a great theory on why. One line of thinking is, for example, if the label is the activity is at least 1 nanomolar, and the model predicts below that, uh, you actually zero out the signal entirely under our current implementation of the bounded mean squared error. So the model knows that it's right in that it doesn't receive any loss, but it doesn't understand how right it is. Which we've definitely seen that under some circumstances, maybe with like the water degradation rate of polymers, for example, or not polymers, but pesticides. That was just one project where they implemented the bounded loss, and it again just like destroyed their performance, and that was sort of what led to that line of thinking. So we're interested in moving into the censored data regime, but we're dry on ideas right now. That's for sure.
Maybe this is something we can talk about at a, meeting that we're planning on having later this week. I'll try and collate some results for you as well.
Yeah, that would be great. Yeah.
John?
Yeah. Just wondering if you've thought about these like large QM data sets that have been coming out as a way to pre-train your model. I mean, like OMOL 25 is like a huge data set, and because it's coming from QM, maybe represents something a bit more ground truth than any kind of public aggregated data set you could find.
hmm Yeah, yeah. So we've seen OMOL, and we did the re-release with I think it was Los Alamos National Lab. So yeah, we've thought about those as well. I think it's either Recursion or Vertex. They have a big foundation model that they pre-trained on exactly what you're describing. So they have a data set that they call large mix with no space. Um, and it's just a giant aggregated data set of QM simulation results. So they have both molecular level features, so like the enthalpy of formation or something like that, and then atomic level features, so like partial charges based on different partitioning schemes, like bond lengths, things like that. Really anything that you could get out of a final converged QM simulation. And they did that pre-training. So I think we've not gone in that direction because others are doing it, and it somewhat relies on your ability to scale. We have access to finite compute, so we can't really compete with organizations like that on, maybe it's a question of running more QM simulations. Yeah, we can't do that. But we also have some theoretical skepticism about the use of QM as the pre-training target. It does feel good to be approximating a solution to the Schrodinger equation and using that as your input. That definitely feels a lot more, physics informed and fundamental. But I think what we have the impression that, almost all of these are exclusively being run at DFT level of theory. Maybe they're getting like final single point energies for some species at much higher levels of theory, like coupled cluster. But QM, almost regardless of the level that you use, up until you really start to spend some node hours, you're going to be introducing systematic error. So it is definitely known that QM simulations have some level of systematic error, moving across the periodic table or particularly down the periodic table. And at least maybe, the presence of systematic error is not as much of a problem as the lack of ability to quantify it. And I think particularly with these really giant data sets, they are so big that you can sort of circumvent this maybe a little bit, but it's hard to say, like the domain applicability of those simulations just based on your choice of functional and your choice of method. So yeah, that's a very long-winded way of saying, we're skeptical about going in the QM direction, and practically speaking, we also benchmark against models that use it as a pre-training target, and we're at least as good, if not better. So we're going to keep mining more this way.
Pat?
Yeah, I can ask questions all day. Um, so you mentioned featurization and different featurization schemes and being able to now integrate these. Do you think that we're going to get to a generalizable featurization if we stay in the land of molecular graphs? I mean, I guess I just look at this as a chemist. I know that benzene and thiophene are very similar. If you look at that from a graph standpoint, they're not. So, how do we do this? How do we get to something that's more generalizable?
Yeah, yeah, that's a good question. I do think that there is something pretty fundamental about graphs that it might just be, the way that we think about these systems that makes this easy to implement or, something like that. But I think there is something fundamental about the mapping of graphs into the computer that means, we're going to be in graph land for a while. And I do think that it will get us there in the end. Whether it's a featurization scheme or like a choice of aggregation function that's going to make that last step, I'm really eager to see. I think one of the top performers in the competition going on right now, they were using a gated transformer. So this is a very high level description that I think the author would be annoyed if they heard me say it this way, but the choice of aggregation function is basically um, attention. So you can achieve both local and global um, attention, for lack of a better word, during the aggregation step of the representation learning. So I think that there's a little bit more room for growth and improvement within this, graph constrained learning space. And I like to think that foundation models pre-trained in this way can hopefully help accelerate movement into that direction. Because, if I had to guess, I would say that the text-based ones like Camberta and Moleformer, they will certainly keep a place because they have some really interesting things that you can do. But if we're going to do attention, I think we should be doing attention on a very clever featurization scheme and on a graph.
Yeah, maybe it's just more how we're encoding the nodes and edges on that graph.
Yeah. Yeah, and I think again, actually circling back to the example you had, the graphs fail to capture things like resonance and conjugation. Uh, like a famously bad thing for Chemprop is like pi-pi stacking. So if your molecule is capable of that for like a solubility model, for example, it'll have no idea and the prediction will be really bad in a lot of cases. I've often, there's some groups that have started to go in this direction of hyper nodes. So they'll make fictional nodes that they stick in the graph that are connected to, all six atoms in an aromatic ring, for example, or along an entire conjugated section of a molecule. Um, but I think that again sort of indicates that it feels like Chemprop is a done deal because it is such a routine baseline for people to run, which we're very grateful for. Um, but I think there's still quite a lot of room to run, and we're optimistic that V2 will help facilitate that exploration.
Are you exploring anything three-dimensional in
Ah,
terms of
I,
featureization?
I like this question because this is the one question I can unequivocally answer. No.
Okay.
Chemprop is and always will be a no 3D method. We have a little bit of work in what we are cheating and calling 2.5D. We are aware that, the stereochemistry introduces a lot of nuance. So like, can we create some sort of an encoding that, on an atomic level can reflect the 3D configuration, just for that individual stereo center? But no, we're leaving 3D to like Unimol, for example. So Unimol is another great. They've just also come out with foundation models. They're a 3D based message passing neural network, um, and they're fantastic as well. You pay a lot to go to 3D. So if you want to be invariant to like translation and rotation, you're doing a lot more math. So like fine-tuning Unimol versus fine-tuning Chemprop is like go get lunch versus go on vacation. So for that reason, we're not going to go that way. But again, there's people doing a really good job of that already, and Unimol is there and pretty performant. So yeah, we're strictly 2D, except our little adventure into what we're calling 2.5, but that's forthcoming.
Yeah, I see their papers where they're talking about training on, hundreds of A100s, and I'm like, no.
Yeah, yeah, yeah. So actually, it's funny you mentioned that. So a fun brag that I like to have. I'm going to turn my webcam here. I have to turn off the. So that's my computer. Okay, it's blurred. Hold on, let me turn that off. Blur my background off. That's my computer. All of the models in this Chameleon paper were fine-tuned on that computer. The initial pre-training was done on a box with 8 GPUs in it. So we're very fortunate to have that, but all of the fine tuning is capable of being done on a local machine, preferably with a GPU, but a CPU if you're patient. Because we also, back when Unimol first came out, a lot of our funders were chomping at the bit. They're like, this is the new thing. This is really great. We're very annoyed that we have to have AWS set up just to be able to fine tune it. So. We haven't talked about it today, and it's not in the paper, but the scale aspect of Chameleon was a consideration during the initial development. It's not impossibly large, partially because we want to be able to train it in a reasonable amount of time.
Alrighty. I think we're at time. So unless anyone has any last minute questions, I'll give you 5 seconds to make yourself known. Um, yeah, sure. Let's thank Jackson and thank him for being our first brave speaker. There's a lot of scary faces in this room, so applause to Jackson for enduring. Um,
No, you're all nice.
um, Yeah, really great talk. We'll be posting this on YouTube following. I'll send this to Jackson to make sure he agrees. But this will go on YouTube for posterity, all going according to plan. So the yeah the this won't be lost to the mist of time. So yeah, thank you again, Jackson. Really appreciate it.
Thank you. And again, I'm uh, uh, eager to collaborate. So I know we have a meeting coming up, but if anyone else has thoughts, please reach out. And I'm more than happy to send along my email for that, as well as a copy of these slides if anyone wants to dig back in at a later date. Everything here is good for linked public release. So I'll make a link for that as well, and I'll send it to you, Hugo.
Yeah, that's perfect.
Perfect. All right.
Thanks again, Jackson.
Thank you,
Have a
everybody.
lovely
Bye
rest of your
now.
holiday. Thanks people for giving up their holiday time.
All right.